So today we are going to introduce a new circuit element, the inductor. And the inductor is a pretty important circuit element because it represents a form of temporary energy storage in our system. Okay. So I'm going to hit you guys with a little bit of background information. If you've had Physics 202, all of this is old hat. If you haven't had Physics 202, this is all new. So you're going to have to just take a little bit of what I'm talking about on tape. Okay. But let's say that we have a section of wire that's a part of a greater circuit. And this section of wire is carrying a constant current I. So whenever we have movement of electrons, we are going to have a magnetic field. And the magnetic field is going to curl around the path that the electrons are taking according to the right-hand rule. So if our thumb is in the direction of electron movement, the field is going to curl around in the direction of our fingers, and I'm going to attempt to draw that. So if this green line here is going to be our field, we would see it coming out of the page above the wire and going into the page below the wire, and it's just forming little loops. Okay. Right. So this is a little bit of background information. We're getting, let me write this out here. So this is our magnetic field. So this could be considered our B field or our H field, and it does not matter to me whatsoever that you guys don't know what the hell either of those things are. It's not important for what we're talking about here. All right. So now let's go down here a little bit. Let's talk about an inductor. So let's say that I have a cylindrical core, like so. So this is going to be my core material. And I wrap a wire around this core, giving it numerous coils. Like so. And then I pass some current I through this coil. I'm going to be generating a magnetic field. And what the coil is doing is concentrating that magnetic field inside that core material so that we have a concentrated magnetic flux, field lines that are going through our core like so, right? So this is our magnetic flux. Our coil has n number of turns, and that concentrated magnetic field is a form of energy. So the more coils we can wrap around this cylindrical core, and the larger the current that we pass through that wire, we're storing more and more energy. Okay. So this is what's called a solenoidal inductor. There's another commonly used arrangement, which is called the toroidal inductor. And I can't draw for crap, so bear with me. So imagine we had a donut of core material. And once again, we wrap a wire. Around our core material. Like so. And we pass a current I through the wire. We're going to generate some magnetic flux again, but this time it's going to be forced for all of it to stay inside our magnetic core or inside of our core material. Okay, so this is another form of an inductor called a toroidal inductor, which I think I already said. And these are the most common forms of inductors that you can buy. If any of you have ever cracked open your computer case or anything like that, you've probably seen a ceramic ring with a wire wrapped around it. That's an inductor. You can actually go make an inductor. In fact, when you guys are doing your labs and we start using the oscilloscopes, because we're going to be looking at time varying quantities from here on out, you can actually mess up your measurements by leaving your oscilloscope probe cables coiled up because you're adding inductance to the system. Okay, and heaven forbid that you run your other scope probe through that coil, because then you're going to be inducing currents and voltages on your secondary scope probe, really messing things up. So you want to make sure that you're going to be dealing with long straight pieces, all that kind of good stuff, to avoid introducing too much inductance. Okay. So as I mentioned a moment ago, these inductors are forms of temporary energy storage for circuits. Okay. The energy storage comes from the fact that we are concentrating the magnetic field into a small region of space. And there is a relationship between the magnetic flux, the inductance of our device, and the current. And that relationship is as follows, right? So our magnetic flux, whose symbol is phi b, is equal to our inductance L multiplied by our current I. So we can rearrange this slightly and say that our inductance is simply the ratio of the magnetic flux to the current that is generating the magnetic flux. Okay. Magnetic flux has units of Webers. Current obviously has units of amps. A Weber is nothing more than a volt second. So we have volt seconds per amps, and we call this unit the Henry. I honestly don't have the foggiest clue who this unit is actually named after. Yes, Owen. B, capital B. So this is something that I've always been a little bit confused about. Typically, when I think of inductance, I think of Faraday's law of induction, which we're literally going to talk about here in a moment to figure out what our current voltage relationship to this thing is. So there is a fundamental law called Faraday's law of induction, and yet for some reason the units of capacitors, which we're going to talk about on I guess, next Wednesday, because we have Monday and, excuse me, Friday and Monday off of the Easter break. The units of capacitance are the farads named after Faraday for whatever reason. And inductance is named after some dude named Henry, who I don't know what he did. So whatever, sometimes things are weird.
Did that say VS or V times?
V times S. Yeah, so a Weber is a volt second, and then a Henry is a volt second per ampere. All right, so speaking of Faraday's law of induction, which is going to be an important thing, so let's write this here. Faraday's law of induction states that an electromotive force, which is just a fancy word for voltage, and your physics professors would absolutely hate me for saying that, but all voltages are electromotive forces, is given by the derivative of, let me use the same symbol here, the magnetic flux as a function of time with respect to time. So effectively, anytime we observe a change in flux, we should induce a voltage. And many of you have experienced this. I would, not to be sexist, but probably every woman in this room has experienced it. How many of you have unplugged a hairdryer while it was still turned on? Nobody? Wow, okay. How many of you have unplugged something while it was still turned on and seen sparks? That is Faraday's law of induction. What is happening is that when you unplug your electrical cord, the amount of current that is flowing is changing so rapidly that the voltage induced is large enough to literally ionize the air molecules in order to maintain that current flow for a short amount of time. Okay. So if you ever unplug something while it is still turned on and you see sparks, you are literally witnessing Faraday's law of induction in action. If you play an electric guitar, it is the exact same thing. Faraday's law of electromagnetic induction is literally what translates the mechanical vibrations of your guitar strings into an electrical signal through your pickup. Your string is slightly magnetic. As it vibrates, it generates a changing magnetic flux, which is picked up by the coils in your pickup, and a voltage is induced across that coil, giving you a signal that can then be amplified. All right, so what does Faraday's law of induction have to do with what we are talking about? So let's do some simple substitutions here, right? So our electromotive force is, like I said, just a fancy word for voltage. So we're going to replace that E with VL, the voltage drop across our inductor. And that is the derivative of the flux with respect to time, right? So the derivative of the flux with respect to time. Well, flux, looking up here, is just our inductance times our current. So if we assume our inductance cannot change, we're going to get the following relationship. L, our inductance, times the derivative of the inductor current with respect to time. I'm going to call this equation 1. This is our first relationship. Our voltage is equal to L di by dt. So If we have a simple inductor, by the way, this is our schematic symbol for an inductor. It's literally representing a coil of wire because that's all an inductor is. Our inductance has some value L. Here's the voltage drop across our inductor. Here's the current flowing through our inductor, and those two quantities are related by the expression above. So there are actually several critical pieces of information about the behavior of an inductor that we can glean from this relationship. So if I have a constant current flowing through my inductor, what should the voltage drop across my inductor be? 0, because the derivative of the current would be 0, and L times 0 is 0. Okay. So actually, let me rewrite this. In a DC circuit, inductors behave like short circuits. Okay. I want to repeat that because you guys have a homework problem. I think it's homework 12, problem 1. That is literally a DC circuit with several inductors, and I get probably 5 questions a quarter on how do I analyze this thing. You make every inductor into a wire and you just go on about your day. Okay, it's all you have to do. Doesn't need to be any more difficult than that. Okay. So this is a pretty important thing, so I'm going to put an underline under it. The next thing that we can glean from this mathematical statement about the behavior of an inductor is going to take us a moment to kind of figure things out. Okay, so let's say that I have the following current waveform for an inductor. So this is going to be IL this is time. And over here, we're going to plot VL as a function of time. Okay. And let's just say, for the sake of argument, that the inductor that we're talking about has a value of 1 Henry so that the math is really easy. Oh, let's say that this is 2 seconds, 4 seconds, 6 seconds, 0 seconds. And this is representing, 1 amp current, right? So I want us to figure out what the shape of the voltage waveform is going to look like here. So we have a piecewise function for our inductor current. It is linearly increasing from 0 to 2. It is constant from 2 to 4. It is linearly decreasing from 4 to 6. So we should expect to see 3 different voltages associated with each of the 3 different intervals of our current, right? So what is our voltage going to look like over the time interval from 0 to 2? Give me a number. 1/2, half of a volt. Constant 1/2 of a volt. L is 1, and our derivative, which is just the slope of this line, is 1/2. 1 times 1/2, I believe pretty strongly, is 1/2. I can do that math in my head most days. right? So we have a voltage of 1/2, put that here, from 0 to 2. Now let's consider the interval from 2 seconds to 4 seconds. What should our voltage be? 0, because our current isn't changing over the interval from 2 seconds to 4 seconds. So we're going to see that our voltage immediately falls off down to 0 until we reach 4 seconds. What about the interval from 4 seconds to 6 seconds? -1/2. Okay, so we have some basic understanding of the voltages that are going to occur across the terminals of our inductor for a simple time varying current like this. Now, let me ask you guys a bit of a conceptual question. What if instead of taking 2 seconds for our current to go from 0 to 1, it only took 1 second? What should we expect the voltage to do? It'd be larger, right? So if it increased in 1 second, our slope would be twice as much, and so we would get twice as much voltage. Well, what if I make that amount of time it takes for the current to change smaller and smaller and smaller until we get to a point where the current changes instantaneously, right? So what if I had this situation? Our current jumps up from 0 to 1 at t is equal to 2, stays constant, and then goes down to 0 at t is equal to 4. What would our voltage waveform look like? So what's the slope of something that instantaneously changes from one value to another value in the same instant of time? It's infinitely large, right? Because the rise is 1, but the run is 0, right? Slope is rise over run. So if it doesn't take any time for it to change from 0 to 1, then our slope is infinitely large, which means the voltage that we are going to see across our inductor terminals is infinitely large. So we're going to have an infinitely large impulse here at t is equal to 2, and we're going to have a negative impulse t is equal to 4. Who can tell me what the problem is? It's impossible. Very much impossible, right? We cannot generate an infinitely large voltage, positive or negative. If you recall, voltage is the amount of energy needed to move 1 coulomb of charge from point A to point B in a circuit. So it represents some amount of energy transfer. It is impossible for us to transfer an infinite amount of energy in an infinitesimal amount of time, right? So what does that tell us? The current flowing through an inductor cannot change abruptly. We cannot have the current instantaneously change values from 0 to 1 or something like that. So we need it to be a continuous function of time in order for our mathematical model to work. Okay, so we'll write that down. So I'm going to give you guys an example. I'm going to use a mathematical notation here. We're going to wind up using it in a little bit anyway. But I'm going to say that IL at 0 minus must equal IL at 0 plus. Or actually, let's generalize this. T minus and T plus. So did you guys use the plus and minus notation when you were doing the limits and all that kind of stuff in your calculus classes? So when we're approaching from the left is minus, and when we're approaching from the right is plus, same thing going on here, right? The current has to be a continuous function. So if we look at it from the left and from the right, it has to equal the same value. Always, always, always for an inductor current. If it doesn't, we're literally violating the laws of physics. Okay, so just to recap things here, we have this first relationship. The voltage drop across an inductor is equal to the inductance times the time derivative of the current. From that single equation, we were able to infer that in a DC circuit, the current, our inductor behaves like a short circuit because the voltage drop will always be 0. And we were able to infer that the current through an inductor cannot change instantaneously. Okay. What we're going to do now is we're going to introduce our second equation by simply algebraically rearranging this guy, right? So if I have VL is equal to L di by dt, and I multiply both sides by dt and divide both sides by L, what I'm going to wind up getting is DIL is equal to 1 over L VL dt. And so now I'm simply going to integrate both sides. So the integral of DIL is going to be IL. Assuming that my inductance cannot change, we're going to have 1 over L from negative infinity to some later point in time we're interested in of our inductor voltage. And I'm using this T prime notation here as a dummy variable for time because T is in my limits of integration. Okay, so realistically, we don't have access to what the inductor was doing at the beginning of time. T is equal to negative infinity. So we can split this into a slightly modified relationship. 1 over L times the integral from T naught, where T naught represents some point in time where we know what the inductor current is, to some later point in time T, of VL T prime dt prime plus IL at T naught. So this is our second relationship. All this relationship really is our first relationship algebraically rearranged, okay? It does tell us something interesting though. The current value of let me rephrase that. The present value of the current flowing through an inductor depends on past values of the current flowing through the inductor. So in a sense, inductors have a little bit of memory, right? This is unlike a resistor where it's just going to be whatever it is at any given point in time. We have to know what the past value of the inductor current was in order to figure out what it is at any other point in time. Okay. All right, so Let's see. Let's talk about power. So the power absorbed by an inductor is simply the product of the voltage drop across an inductor and the current flowing through an inductor, because that's literally what the definition of power is. But we can substitute in our relationship for VL of T, equation 1, and find that our power will be L IL DIL by dt, which is relationship number 3. So we can determine the power absorbed by an inductor by only knowing the current. Current is the most important piece of information we can know about what's going on with an inductor. And our last relationship will be for energy. So the energy stored in an inductor is the integral of the power absorbed by said inductor. Substituting in relationship number 3, we have the integral from negative infinity to t of L IL DIL by dt. All of these t should be primes, dt primes, and these two dt primes effectively can cancel each other out, giving us the integral from L, there's going to be the integral of L IL D IL. So what should my limits of integration here be? You guys have taken math way more recently than me. Exactly right. So IL at negative infinity, IL at t. So what's the integral of effectively a constant times x with respect to x? Exactly right. So in this case, this will reduce to 1/2 times L, our constant, times our variable squared. We are making an assumption here. It's a very easy assumption to make. At t is equal to negative infinity, the beginning of time, or the beginning of the inductor's existence, there wasn't any current flowing through it. Pretty easy assumption to make there. So we can see that the energy stored by an inductor is related to the current flowing through said inductor, which is exactly what I told you at the beginning of class. It all has to do with the current's ability to generate a magnetic flux. Okay. All right, so this is relationship number 4. Just to be clear here, you're not going to get an equation sheet for exam number 2. So I am going to expect you to know these 4 equations. Telling you that now, so that there's no surprises or anything like that. On 1 week from today, we're going to talk about capacitors. I'm not done with this lecture yet, but we're going to talk about capacitors. And I'm going to review these concepts that we talked about here today. And the reason that I'm going to do that is because the capacitor is what's known as the electrical dual of the inductor. So literally, every relationship that we just had here for our inductors, we will have the exact same relationship for capacitors, except that everywhere we see an L, we're going to replace it with a C. Everywhere we have voltage, we're going to replace it with current, and vice versa. It is literally the exact same set of equations. So I am telling you emphatically, you really only need to remember one set. The other set is the same damn thing. So stop being whiny babies about having to memorize 8 equations. It's really only 4. Okay. All right. So last things that I want to talk about today. You will occasionally have problems that involve multiple inductors. So it might be of use for you to know how to combine multiple inductors into some equivalent inductance, right? So let's start by looking at inductors in series. Let's say that we have a series combination of inductances. So let's call this L1, L2, L sub n, like so. And each of these inductors will have a voltage drop across it. VL1, VL2, let me write that better. All the way out to VLN. There's going to be a total voltage drop across all of these inductors. And some current flowing through all of these inductors connected in series. So it's going to be very similar to what we did with resistors a month ago at this point. We are going to apply Kirchhoff's voltage law and find that our voltage drop V of t is equal to simply the sum of all of those inductor voltages. All of those voltage drops can be expressed in terms of that common current I that flows through all of the inductors. That's going to look like L1 di by dt plus L2 di by dt all the way out to L sub n di by dt. I can group all of my inductances together. So L1 plus L2 all the way out to L sub n di by dt, or simply call this LEQ di by dt, where LEQ is L1 plus L2 plus L sub n. More succinctly, we can simply say that inductors in series combine like resistors. In series. So, not to bore you guys with more calculus and algebra, but how do you think inductors in parallel are going to combine? like resistors in parallel. Great. So not going to bother you or bore you with the math behind that. Okay. Okay. So that is the end of my lecture. I do understand that I've only talked for 45 minutes and we have not worked a single example really. So would you guys prefer to work on your in-class assignment, or would you prefer for me to work some examples to show you how all this crap gets used? Option 2. Okay. So let's say that we have a 0.25 Henry inductor. This is the voltage drop across our inductor. This is the current flowing through our inductor. And we are told that the voltage drop across our inductor is of the form 0 volts for t less than 0. And it is 5e to the minus 4t volts for t greater than or equal to 0. So just for the sake of argument, I'm going to plot this as a function of time just so that we can have some idea of what's going on. So this is VL, here's T. I think I was using blue for voltage earlier, so that's what I'm going to continue to use. So at 0, it instantaneously jumps up to 5. Oops. And then it exponentially decays, gradually going towards 0 at t is equal to infinity. So I want to ask you guys a simple question here. Is this voltage waveform okay for an inductor? So there's a discontinuity in the voltage, right? The voltage was 0 at t is equal to 0 minus, and it is 5 at t is equal to 0 plus. Is this a problem? Raise your hand if you think the answer is yes, this is a problem. You're mistaken. The current through an inductor cannot change abruptly. The voltage drop across an inductor can do whatever the hell it feels like. Just to remind you guys, scrolling up here, in the very simple example that we worked, the voltage was changing abruptly. No problem whatsoever, okay? So that is a fundamental thing that you're going to need to remember. It is only the current that cannot change abruptly. The voltage across an inductor can do whatever it needs to do. Okay. All right. So let me continue defining our problem statement. If IL at 0 is equal to 2 amps, I want us to determine A, the inductor current IL of t. So I'm looking for a mathematical function here. B, the power absorbed by the inductor. EL of t. And C the energy stored by the inductor. WL of t for t greater than or equal to 0. So if I give you voltage and I'm trying to find current, which of the 4 relationships do I need to use? The second one, right? So IL is equal to 1 over L times the integral from T naught to T of V of L T prime or VL of T prime dt prime plus IL at T naught, right? So if I have voltage and I want current, this is obviously the relationship that I need to use. So 1 over L is going to be 1 over 0.25. A Henry is a volt second per amp. So I'm going to put volt seconds down here and amperes up here. Everybody okay with that? So the integral from, so what's T naught in this case? 0, because it's the time where I know what the inductor current is, which I specifically say at 0, I know what it is. So this is 0. I'm going to integrate to T. My inductor voltage waveform is 5e to the minus 4t volts. Remembering to put my primes plus my 2 amp initial condition. So one thing that I can do to make my life a little bit easier here is I'm just going to pull that 5 volts out of my integral, right? So I'd have 5 volts times an amp over 0.25 volt seconds. Now I'm left with the integral of e to the minus 4t. So how do I do the integral of e to the alpha? Just actually, I can put it on the record it. So this is a quick side note type thing here. This is the level of calculus that I expect you guys to be able to do. The derivative of e to the alpha t is alpha e to the alpha t. The integral of e to the alpha t dt is 1 over alpha e to the alpha t plus c, right? So in this case, alpha is -4. So 1 over -4. What are the units? What was that? Right, but I'm asking what are the units on alpha specifically? 1 over second, absolutely. So the argument of the exponential function needs to be a unitless quantity. If time is measured in seconds, then alpha must be in per seconds, so that the exponential is just going to return a number. Okay. So 4 per second. E, let's see, to the minus 4 t prime evaluated at t in 0. So let's get rid of some of these things here. So my second and my per second cancel each other out. My volt and my volt cancel each other out. And I have 1/4 multiplied by 4. So that comes out to be 1, leaving me with a factor of -5 amps. And then evaluating my e to the minus 4t at t in 0. Are we okay with the calculus? Yes, Grayson. Thank you. I forgot it. So that is critically important. So thank you for that. Absolutely correct. All right, so e to the minus 4t prime evaluated at t is simply e to the minus 4t. E to the minus 4t prime evaluated at 0 is 1. All right. So I have -5 amps times -1 is going to look like +5 amps plus 2 amps gives me 7 amps minus 5 e to the minus 4t. And actually, let's just do this whole thing is measured in amperes. So that is my current. How did you feel about that level of calculus? Hard as it's going to get. Legitimately. Okay. So part B. We're asked to figure out what the power is. How are we going to do that? The power equation. It seems like a reasonable thing. Well, let me ask you a question. I'm going to scroll up here so that we can see the power equation. Am I going to do the product of voltage and current or L times the current times the derivative of the current? Either will work, but the product of voltage and current is going to be the easier thing to do because we already know the voltage and we just found the current, right? So don't kill yourself doing math that doesn't need to be done. Let's just multiply these two things together and call it a damn day. So PL is VL times IL. So that's going to look like 5e to the minus 4t volts times 7 minus 5e to the minus 4t amps. So 5 times 7 is 35 e to the minus 4t watts. And then 5 times -5 is going to be minus 25 e to the minus. So what happens when I multiply two exponentials together? The arguments add, right? So -4t plus -4t is going to look like -8t watts. Donezo. Easy enough. And lastly, C, the energy stored by the inductor, W over L, is 1/2 L times IL squared. So that's going to be 1/2 times 0.25 volt seconds per amperes times 7 minus 5 e to the minus 4t amps quantity squared. So now I'm going to oil out that thing, so 0.25 volt seconds per amps. So 7 amps times 7 amps is 49 amps squared. 7 amps times -5 e to the minus 4t is going to be -35. That's going to hit twice, so we're going to have -70 e to the minus 4t, and then -5 times -5 is going to look like +25 e to the minus 8t. And this whole thing has units of amps squared. So let's see here. Half of a fourth is an eighth. So that's going to look like 49 eighths minus 78 e to the minus 4t plus 25 eighths e to the minus 8t. And let's just look at the units here really quickly. So this amp is going to cancel out one of those amps. So we have volts times amps times seconds. A volt times an amp is a watt. A watt times a second is a joule, which is a unit of energy. Exactly what we were expecting. So the units here are in joules. Check. Any questions, comments, or concerns? So on your exam, I can either give you something like that, where I give you a relatively straightforward mathematical expression. I don't know that I've ever given anything that wasn't an exponential function, just to be clear. Or I might give you a graph problem. So just for the sake of argument, let's pull up one of your practice tests real quick to see what kind of junk I have thrown at you all in the past. So random exam 2. All right. So here's a graph problem. In this problem, you're given the voltage. Let me see if I can find one where you're given the current first, just for the sake of argument, because this is largely exactly what we just did, but in graphical form. I mean, it's not going to be a problem per se, but this is an inductor. This one represents the current. Okay. So let's look at number 17 here. If IL of 0 is 0.8 amps, the voltage drop across, or over the inductor, across the inductor, whatever, at T is equal to 105.328 milliseconds is going to be closest to what? So how do you think we'd figure that out? So we're given current, we want voltage. Yeah, absolutely, right? So the voltage drop across an inductor is L di by dt. So because I want the voltage drop at 105.328 milliseconds, I believe that I should be looking at the slope over this interval because it contains the time 105.328 milliseconds, right? So I have a slope of y2, which is 0.4 amps, minus y1, which is negative 0.2 amps, divided by x2, which was 120, milliseconds minus X1, which is 100 milliseconds. So that looks like 0.6 amps over 20 milliseconds. I multiply that by L, so 0.3 volt second per amps times 0.6 amps per 0.02 seconds. The amps cancel, the seconds cancel. I can't do that math in my head, so I'm going to use the calculator. Zero 0.3 times 0.6 divided by 0.02. 9 volts. It, not trying to rant or sound like more of a jerk than usual, but it blows my damn mind how often a problem this easy gets missed. Just saying. Not intended to be hard by any stretch of the imagination, but it gets missed quite a lot. If we look at problem 18, we're trying to find the power absorbed by the inductor at T is equal to 168.912 milliseconds. So what should that answer be? You should be able to look at this and figure it out. No math involved whatsoever. 0. Why is it 0? Yep, the current isn't changing, so the voltage is 0, and if the voltage is 0, the power has to be 0. Yep. For number 19, we want the energy stored by the inductor at T is equal to 16.847 milliseconds. So what are we going to do there? Yeah, 1/2 L times IL. IL is 0.8. So WL of, I don't know, 16 milliseconds or whatever the hell it was, is 1/2 times 0.3 volt seconds per amp times 0.8 amps quantity squared. Throwing that into my calculator. I get 96 millijoules, excuse me. And I'll be damned. That's what the correct answer is. Okay. So we have put into use all of the 4 equations. The only thing that I have not given you guys an example problem of is inductor combination. Do I really need to do that? Because it's the same thing as resistors. Okay, I didn't think so either. I just wanted to make sure. I'm going to stop ranting now. You guys knock out your in-class assignment, and then I hope you have a great Easter break.